Good morning. Today's lecture is a continuation for our first revision lecture. This is part 2 of our revision. Till the previous lecture, we went through chapter 1 to 5. Now we are going to start from chapter 6, deep foundations or piles in specific. What is important about chapter 6, deep foundation, is the types of deep foundations. We have many types of deep foundations, and this may result in lots of confusion because you may find lots of types in many references. We need to, as we said before, in any other type of foundations, we need to know what are we classifying this type into. Is it the method of construction? Is it the method of design? Is it the type of material? Is it? There are lots of classifications, so don't be confused. If I say that at the beginning I have deep foundations and shallow foundations, this is the major categories of foundations. Within deep foundations, I may have piles. This is the major type of deep foundation. Of course, there are other types, but let's say the deep foundations in our syllabus here is equivalent to the word piles because this is the major type that we are classifying. What are piles subdivided into? Here you will find board piles, driven piles. So we are speaking about the method of construction. So based on the method of construction, they are either board, where we can drill and then add the pile inside, or driven, where we bring the pile precasts and from outside and insert it inside the soil. So these are the major two types of piles. We have another type, it's called caissons. Caissons is not a category of piles, it's a category of deep foundations. So we can say deep foundation is divided into piles. Piles are either bored or driven. And it's also divided, classified into caissons. Caissons, you can consider it a type of pile, but it is a very big type of pile. If I have, instead of having a small circular pile, I have a very big pile, and in this case I don't need to make it full from inside. Maybe I would have it as a ring. In this case, it is a caisson because it is a very big pipe that is hollow from inside. It may be circular, it may be square, it may be subdivided into chambers like this case that we have. So these are mainly the types of deep foundations, and as I said, deep foundation is mainly in Egypt piles, and piles are either driven or bored. We also have caissons that is a type of big piles that we can use. Where to use the deep foundations and where to use the shallow foundation, we said it depends on the loading and it depends on the type of the soil. If I have very minor loading, very small loading with good soil or moderate soil, then shallow foundations are okay. If the loads increases and the soil is still not very good, then in this case I may need pile to take the load from the upper layers to the stronger layers below. If loads increases much more, in this case I may need caissons or very big piles that would carry the load to the bedrock below. This is of course normal in case I'm constructing a skyscraper or something like this. When to use deep foundations? When I have the bearing capacity is not adequate, when I have the settlement is excessive, when I have tensile loads, because as we said before in shallow foundation cannot carry tensile loads. So if I have tensile load, or if I have horizontal load that is more than the friction between the shallow foundations and the soil, then in these 4 cases I need to use deep foundation, and in this case I must use deep foundation regardless of the cost or the expenses of the construction. So these are, if I wanted to categorize pile, if I categorize them based on pile material, then I have lots of categories: concrete, steel, timber, and so on. If I categorize them according to their construction method or method of installation, then I have board piles, or I have let's see the other one here, according to the method CFA. This is also another type of board piles where I drill the hole, then pour the concrete, and then add the reinforcement. So here is the problem of the CFAs. The CFA is very good and very quick, but its problem is that I cannot guarantee that reinforcement will be able to penetrate the concrete and reach the bottom of the pile. Usually I use it in piles that are not subjected to tension or horizontal load. I mean, there is no moment on the pile, so in this case I don't need reinforcement a lot. I just need a little bit of reinforcement at the top, so CFA would be my best choice. Another type is the driven pile. Driven pile, of course we said driven. I bring the precast pile, I hammer it till I reach the bottom. The problem of this is that maybe the soil is a little bit stiff, or there is some obstruction on the way. So in this case, not all of the pile will penetrate the soil, and in this case I will have to cut whatever remaining on top of the ground. So this is the driven pile, how we construct the pile. We said that to design the pile, then we need to know what are the factors that help me in the carrying capacity of the pile. I have something called end bearing, where the pile is bearing at the bottom of the pile on a good ground. I have also the friction, the skin friction here. So this skin friction represents the friction between the soil and the shaft of the pile. So my design will be based on 2 factors or 2 categories. The first one is the friction between the soil and the shaft of the pile, and the second is the end bearing of the soil. So whatever equation I will get, say here Q ultimate, it is the Q due to friction plus the Q due to bearing. So you need to understand in any equation where is the term related to the friction and where is the term related to bearing. To get a load, I always multiply a stress by an area. So the area will define which category I am using. If I'm multiplying my equation by the area of the pile, the cross section of the pile, then in this case I'm dealing with the bearing capacity of the pile. If I'm multiplying by the area of the sides of the pile, then this is the frictional capacity of the soil, because the area of the side is the interface between the pile and the soil in case of friction. Here the first method of design is based on the equation given in the Egyptian code, the static equation given in the Egyptian code. It contains these two portions that I've said, I discussed, the bearing and the friction. So here this portion is multiplied by area of pile, then it is the end bearing, here the sides, area of the side, then this is the friction. Here are lots of parameters. These parameters, each one comes from a specific table. Of course, in the exam you don't have, you're not going to have these tables, but you are going to have the parameters if this is one of the problems in the exam. And so on. These are the tables where I can get all of my parameters. And once I get the parameters, I can just go to an example where I have I have a pile penetrating 3 layers. In this case, I need to calculate 4 things. One related to the end bearing layer, which is the sand here. The sand here has end bearing and have some friction for these 2 meters. And then the upper layer, they don't have end bearing because the pile penetrates them fully, and it's only the friction between the sides. So I will calculate the friction for this layer, the friction for this layer, the friction for this layer, plus the end bearing. So I have here 4 things to calculate. I get the 4 things, I use the tables, or in the exam it will be given, and I calculate the 4 parts and then add them together to get the ultimate capacity of the, here is the ultimate capacity, because the equation gives me the ultimate capacity. I divide the ultimate capacity, which is the sum of the 4 portions, by the factor of safety, which is usually 3. I get the allowable capacity. Once I get the allowable capacity, I always calculate something called the structural capacity. The structural capacity, which means the capacity of the pile as a concrete section, as if it is a normal column. For a normal column, I multiply FCA for concrete with the area of the pile. I get a value, this value. If this value is less than the allowable, not the ultimate, if it is less than the allowable capacity of the pile, then I use the structural capacity of the pile. Another example, very important, is the graphical presentation, because the previous method was only applicable for piles up till 60 centimeter in diameter. More than 60 centimeter, I need to use another method. One of the other methods that I can use is this graphical presentation of the pile. I want to reach this curve. This curve represents the relation between the load and the settlement of the pile. It is equivalent to a full-scale loading test for a pile. But instead of doing a full-scale and spending a lot of money, the code gave me an approximate way to draw this approximation. Of course, it is not a curve, it is a few lines connected together, but in a way they are very good in presenting the behavior of the pile when subjected to loading. How to get this? If you remember, we said that piles has two parts. for loading, a part related to friction and a part related to end bearing. So the code will give me these two lines or these two curves. One of them represents the end bearing, and the other gives me the friction. So to draw these two lines or do these two charts, I need only 1 point for each. If I know point A and I know point B, then point A I connect it to the 0, 0 and move horizontally, I get this chart. Point B connected to the 0, 0 and move horizontally, I get this point B. So if I know point A and point B, then I can draw both charts. How can I know a point on this graph? If I know the settlement and the load corresponding to this settlement. So the code is going to give me this point in terms of settlement and in terms of loading. But you know that we have this will depend on the type of the soil. So the only classification the code would make is to tell me that point A, in case it is sand, take it this value. In case it is clay, or in case it is cohesionless, take this value. In case it is cohesive, take the other value. So let's go first for we need, the code is going to give me now this point, which is the settlement corresponding to point A, and will give me the settlement also corresponding to point B. So SF, which is the settlement corresponding to point A, is 5 to 10 millimeter or 10% of diameter. So I take 1% of the diameter. I will calculate it, say the diameter is 80, so 1% is 0.8 millimeter. So 8 millimeter is in between 5 and 10, so it is okay, I can use it. If it is more or less, then I would take it something in this range between 5 to 10 millimeters. So this is SF, and it does not depend on the type of soil. SB for bearing, it depends on the type of soil. Is it cohesionless like sand or cohesive like clay? In this case, I would take it 15 centimeter or 5 centimeter, and so on. The code will give me the other direction. It will give me the stress or the load in case of these 2 points, which point A and point B represents the failure in case of end bearing and friction, the failure load. So which is called the ultimate skin friction and the ultimate base resistance. So the ultimate skin friction, which is this one for point A, this is the ultimate skin friction, which is the ultimate resistance related to the friction between the soil and the pile. So he gave me a table for 11 or for 10, and for the other there is another table, and so on. So I use the table. I go to the settlement, which is the maximum settlement. I will take the value. Of course, in an exam you would either get the numbers directly, or you would get the chart drawn. Once you draw this, you know point A and point B, you can draw these two charts. Then the remaining is to sum up these two charts into one chart. To sum up here 0, 0, it is the sum is 0. So I know the first point. The second point is here. This is point A. I go vertically down. I get the value of this point. Add this value plus this value. I will get this value. So now I have this other point. So now I have this point K. Once I get point K, I go to the other next point, which is point B. Point B, I get the value here. Of course, this value is equal to this value. I sum up these two, I get the point C. So now I have point C C and point K and point 0. I connect this, and go horizontally, then I have the sum of these three. If I have the sum of these 3 points and I have the upper chart, I can delete the other 2 charts. This was my target from the beginning, the chart that is representing the loading curve of the pile, and this is the approximation of the loading curve of the pile based on the data given by the code, the Egyptian code. So this is my important chart. Once I get this chart, I can use it. How can I use it? This is the ultimate load for the pile in general, based on friction and end bearing. This is the maximum. If I know the maximum, I can take a factor of safety. Say I need a factor of safety of 3. Then this value, I will divide it by 3. Maybe I will get this, let's change the color. I would get this line here, this line instead. So this value, I divided by 3 to get this value. So this value is the ultimate divided by the factor of safety. So this is one point. The other point is related to the settlement. We know that the maximum settlement that is allowed for any building is 2.5 centimeter in case I'm using isolated footings. So 2.5 centimeter, I go from 2.5, suppose here is the 2.5, here is the 2.5, I go vertically up, where I said I don't have these two now. I will go up, vertically up till I reach this point. This point I intersect with the curve, my target curve. I go horizontally, then I get another load. So I have this load based on the ultimate. This is factorized from the ultimate, and this load is coming from a settlement of 2.5. Of course, from what I have shown here, this value is less. So this will be my critical value. I will take this value. But if this value here, if 2.5 is here and I just go to this level, so this will be my critical value. So based on comparing these two loads, I know the load of the what is the design load, the geotechnical capacity of the pile, based on what the soil can carry in case of friction and in case of end bearing. Once I finish this, I get a load. So this is the load that is carried by the pile. What is this adequate? No, I should also check the pile as a concrete section, similar to what I have done in the previous method. I will just get if I know the diameter of the pile and I get the area of the pile multiplied by FCA of the concrete, I will get a value. I will compare this value with the minimum of these two to get the load that is carried by this pile. This is exactly what I have said here. This is how this is done, and here is the structural capacity, the geotechnical capacity based on both both values was 9,000 something. When I checked the structure, it was 5,000 something. Then also here the structural capacity is the governing capacity. So now we know two methods. There is another method which is not related to any diameter. It is just related to the type of pile, because it is a dynamic. The previous two methods were static methods. This is called the dynamic method. It is based on the values given by another dynamic method of testing of piles, which is the SPT, standard penetration, is a dynamic method. I use vibration, I use hammering to get the value. So this is a dynamic way of testing of the soil. So it is used in this equation. This equation, the first thing I have to check to notice, it gives me directly Q allowable not not Q ultimate. So this is the allowable. Don't divide by a factor of safety. So this is the equation. There is part of the equation that is multiplied by pi r square. So this is the area of the pile. And there is another part that is multiplied by the area of the sides. This part, of course, because it is multiplied by the cross-section of the pile, the cross-sectional area of the pile. So this is the end-bearing portion, and this is by the area of the shaft from outside. So this is the frictional portion. So these are the two portions of the capacity of the pile. And it gives me directly the allowable, not the ultimate. If I tell you what is the ultimate, then you should multiply this value by a factor of safety, not divided by a factor of safety. And so on. I apply. Here, from what you can see, I need just to know what is N1 and what is N bar. To know what is N and what is N bar, this is important. N is the value of N at the pile tip, but I don't just go to the pile tip. I go below the pile tip with 1 diameter. I go up the pile tip with 3 diameters. Any value given here, I take the average of it. Here it is only one value, so it is 21. This is the value of the SPT at this. So N value, my N here is 21. If I have 21 and maybe 23 at this point, then I will take the average of 21 and 23. It will be 22, and so on. N bar is the average of all the N values from the start of the pile to the end of the pile. So any value given here, I add it and divided by their number, I get this value. So this is N. So now I know N and I know N bar and I know N. I just substitute in the equation. I get the allowable. Why I multiplied here by half? I multiplied here by half because it is a board pile. This example is a board pile, and I said the equation is for driven piles. So if I want the value that is, I need some conservative value for the board piles, then I only take half of this value. So this is the normal equation. I multiply it by half to get the allowable value for a board pile. And so on. Once I finish, I calculate the structural capacity. Here the structural capacity was very high, and I took the geotechnical capacity to be my pile capacity. What about tensile loading of the pile? The tensile loading of the pile is the value of the friction between the pile and the soil only. So if I need, I want to get the T allowable in case of tension, a tensile load, then I will neglect the end bearing. I don't want the end bearing because the end bearing is only bearing in case of vertical loading in the direction of the gravity. But if I am pulling the pile, then in this case no bearing will happen, but the own weight of the pile may help a little bit. So I can add the own weight of the pile to the if I use an equation that would give me T ultimate, which is the ultimate capacity similar to the first equation or the first method or the second method, they give me the ultimate load. I divide the portion for the friction by the factor of safety, and then I add the own weight without any factor of safety because it is there. I don't need to put any factor of safety for it. So this will be the allowable. So the difference in calculating the tensile capacity is that I only take the portion for the friction divided by the factor of safety to get the allowable, and add to it the own weight of the pile. Use any equation from the 3 previous equations to get the ultimate tensile or the allowable tensile capacity if I divide by factor of safety. This is an example. Of course, it is the same example, but for a case of tension. Of course, here you find that we don't have any end bearing, just the friction between the three layers. I add them together, divide them by the factor of safety, add the own weight of the pile. This will be my tensile capacity. Of course, if this is the start, this is my start to calculate this example, then I need to check the geotechnical the structural capacity. But here, because I know the structural capacity of this pile from previous examples, and usually in the tension the load is very small, so I sometimes I neglect the structural capacity. But the rule of thumb, you always calculate the structural capacity, compare it to the allowable capacity that you have got from the any method you are using, whether tension or compression, and use the minimum of them. This ends our calculations for the piles as a single pile. This is just for info, how to know how piles will behave in case of lateral load. This is only you just need to know it. It depends on the stiffness of the pile. Will it act as one body, or will it have a bending inside it because it is very long pile? It also depends on the type of soil. Is it clay soil or sandy soil? We know that sandy soil is affected by the vertical overburden pressure, so it increases with depth. The sea, it depends on the internal cohesion of the clay, so it does not change with depth. So these are the important things that you should know, but we usually use computer programs to calculate it. Then I have the static test or the pile load test. The pile load test is something very important because, as we said, you've seen this in the coursework. We have a lot of values that are driven when I get them when I use different methods for calculation. Which one is is best? There is no method that I can say is the best or the accurate. Each one may be accurate in a special case. So in this case, I need to make a full-scale test in any project. This is very important, that once I finish the design and I went to the site and I do a model for the full-scale model for the pile in the site, and I load it till failure. In this case, if I load a pile till failure, then finally I will get something, a curve similar to this. This is the loading curve of the pile. If you remember, this is similar to what we have said before when I was using the graphical method. I said that this graphical method, this line resembles the loading curve of the pile. So this is exactly what we need here. We need just to put our data here. So this is the loading curve of the pile. The maximum I will get here, this will be my ultimate load, and I can use it in the design. I take the ultimate divided by a factor of safety to get a value somewhere here. I take a settlement of 2.5, go vertically and then horizontally to get another load, compare both together, then this will be my geotechnical capacity of this pile based on loading the pile itself. So this is very important because it is exact. Last important thing is the Of course, you have seen this in your coursework, how to put piles together. But what is important in putting piles next to each other, if I have a column like this and I have 7 piles, I will put the 7 piles here all around and 1 below, here 6 piles, here 6 piles. Yani there are lots of arrangements, but what do I expect if I have piles close to each other? If you remember in a previous lecture, I told you, imagine that your pile is like you swimming in a swimming pool. Your legs resemble, the motion of your legs resemble the end bearing, and the motion of your hands resemble the friction. So if you are swimming alone, you can use both hands and both legs freely. But if it is crowded pool, then in this case your hands cannot move freely, but your legs can move. So in this case the end bearing will work very good if I have piles crowded next to each other, but the friction will be affected. So if I tell you what is, if I have here say 5 piles, each pile can carry 200 ton. What is the maximum capacity? The maximum capacity can be 5 multiplied by 200 is 1000. This is the maximum capacity. But can I guarantee? No, I can't guarantee. What can happen? Maybe part of the friction will be lost between these piles here. The interface between the piles will lose some friction. So in this case, the total of these 5 piles may not be 1000 ton, maybe it is 900, 800, 700, depending on what we call the efficiency of the group, how piles are crowded together or away from each other. So this is also an important, what is the geotechnical capacity of the group, or the group efficiency of my piles. I think last thing is the calculation of settlement. Now I know the group of the load of pile, I know the load of the group. Are they going to work together and settle, or are they stay in place? Of course they will settle. How to calculate this? There is an approximate way. The approximate way is to remove the piles and put instead of them a raft at the bottom here, as if this, or a foundation, an big isolated footing at the bottom. So is it at the bottom or is it above the bottom here in this location, depending on what type of soil. If not sand, if I have a frictional an end-bearing soil piles, so I will assume the raft here, or the shallow, the isolated foundation here. If I have a cohesive layer that results in a frictional type of pile, then in this case I will assume it at the lower third of the pile. So this is the location of my imaginary footing, and this is the location of my imaginary footing. Here it is friction or end bearing. If it is end bearing, it is at the bottom. If it is friction, it is at the middle third. I take the distance from this location to the bottom where my stresses can reach. If I have a rock layer, then I know that this edge is from this location to the location of the rock. But if I don't have a bedrock layer near, it is very far away, I will just go to double the breadth. If this is say 10 meters by 15 meters, so 10 meter multiplied by 2, you get 20. So from this point I go 20 meter below, and I put an imaginary line, and I say this is the end of the area where the stresses can reach from this imaginary footing. Similar thing will be done here. If this is my location, I go to the bedrock level, or I go to the twice the breadth here of this imaginary footing, and I start calculating the settlement. This is my equation of settlement. You should know this equation. It is very easy, and the derivation is given here. This equation gives me directly the settlement of this imaginary footing, which is the settlement of the group. This is just a quick. Here also another thing, the lateral capacity of the pile. You should know that when I have a lateral load, always pile 1 here and pile 1 here are the major carrying piles, because they are subjected to bearing on this soil here and friction on this soil here, bearing on this soil here, friction on this soil here. So this is the maximum. The second category is number 2. This is bearing here on this soil, bearing on this soil. The third category is here. This is friction on this soil and friction on this soil, friction on this soil, friction on this soil. But what about the soil here? All of this soil here is distorted. Due to the motion of the pile cap, all of this soil is distorted. It is not in place now, so it cannot carry anything. So the load carried by piles number 4 is minimum. It is the least amount. Last thing is the negative skin friction. This is for your own info. If I have a clay layer, it may consolidate with time. Suppose this is my clay layer that was carrying the pile. Maybe with time it will consolidate, and once it consolidates, it moved down, and once it moved down, it was adhering to the pile to carry it. But what will happen is the opposite. The soil will go down and it will be adhered, it is adhered to the pile, so it will carry the pile below. So instead of carrying the pile, it is being carried by the pile. So if you calculate here a load capacity for this layer that can carry the pile, it will be acting as a load on the pile. This is very important. What is also more important, if the layer is very small, you have a small layer here at the bottom. This is only the clay, and all of this is sand. But because the sand is standing on the clay, so the sand with time will also move down. So all of this will be a negative skin friction or a negative friction on the pile. This is very important, and it can be a reason for problems in any design, because instead of calculating all of this as a carrying layer, it turned with time to be a carried load on the pile, so it is a big problem. I think this is enough for this. The last thing was the quality control. We do quality control test, sonic test on all piles to check any problems in the construction of any pile. So I have a loading, I can do pile load test, but this is very expensive, and I can do this sonic test on the piles, and it should be done on all piles because it is not expensive. The other may be conducted on maybe 1% of the piles, or a minimum of 2 or 1 pile per site. But here it should be on all piles because it is not expensive. The chapter of the pile took a long time in this lecture. We'll go directly to chapter 7, which is the retaining walls and lateral earth pressure. Retaining wall is very important because we said that retaining wall is our other way of doing two soil at different elevations. I have soil here at this elevation and I have soil at this elevation. What can I do? The first thing you should think of is to make a ramp like this. If you make a ramp like this, then this will be the upper layer and this will be your lower layer. This is your first choice. You have taken before the stability of slopes. Slopes are my first choice. But in case I don't have adequate land and I need this area, I cannot, from here to there is the area used by the slope. I don't have it. So in this case, I will remove this slope and put this retaining wall. So retaining wall is my second choice because it is expensive, much expensive than a slope. Slope is just filling material from the site and compacting it, but here it is concrete, reinforcement, workmanship. There is a lot of time and effort and money spent. So these are different types of retaining walls. We said that this is the type that we have studied here. If you remember this lecture, reinforced earth. In reinforced earth, this is a reinforced earth wall. As you can see, it is very small and very easy and does not cost a lot, but it is only it can only be used in case I'm constructing the fill. But if I have something like this, which is an existing soil or rock, I cannot use it, of course, and I have to use other types of stabilizing these slopes. And so on, you are going to go through the types of walls, and as we said, you need to, so don't be confused, a classification of retaining wall based on what? Based on material. This is the classification based on material, based on type of construction, based on design, based on what? So you need to know what are the different types of retaining wall. And this is another type, which is the flexible retaining wall. And we said a flexible retaining wall I think it is similar. Yes, you remember in chapter 8 the shoring system. We said if you refer to the shoring system, you will know that this is the shoring system. A shoring system is a temporary wall that can move a little bit. It will not fall, but it can move, so it cannot be used in temporary works. It can use only during construction, and it can be reused in case it is steel sections, or can be concrete and can be left in the ground depending on your type. So the difference between flexible and rigid, the rigid can be used as permanent walls. The flexible cannot be used as permanent wall. It is just a shoring type that is temporarily used for a period of time during construction and then removed again. We said that to design the wall, we need this time to know what is a lateral earth pressure. The lateral earth pressure is the pressure of the wall. We know the vertical earth pressure. If I have a point here at a depth of h, so the vertical earth pressure is gamma h. But what about the lateral? The lateral is part of this gamma h. If I take the vertical and multiply it by a factor, this factor is called K. This K may be called K naught, K active, or K passive. Here it is K naught because the soil is not moving to the right nor to the left. But in case I have a wall like this, then if I take a point here and a point there, this point is, of course, it is not expected to move this way because how come it will move this way? The wall is expected to move like this. So when the wall moves like this, so this is called an active zone. An active zone is the zone that pushes the wall, because that's why it is active, because it pushes the wall. A passive zone is the zone that stay in place and the wall come to compress it. So this is the passive zone. Usually the K here is called K active and the K here is called K passive. K active is small because it is consumed in motion. K passive is very high because it is increased by the motion of the wall. The motion of the wall compresses this soil, so the soil increases in the properties of it, and it is better. That's why I usually tell you the comparison. This portion represents people invading another country. Here people resisting the invasion, and so usually these who are resisting are very strong, even if they are small in amount. Here they are small in height. Here though they have a bigger height, but their amount, their contribution is more or less similar to the contribution of this passive zone, so the wall stands in place and no invasion happens. This is the normal case. We hope that this happens in reality. Anyway, we'll continue. We have a theory given by Rankin. Rankin said that he will give us the value of K active and he will give us the value of K passive. K active is 1 minus sine phi divided by 1 plus sine phi. K passive is the opposite, the 1 over K active. And he gave us a general equation. Where is this general equation? This is the equation that can be used for C and phi soil. C phi soil, not C and phi. Of course, we cannot use this theory for C soil only. But if we have phi soil or C with phi soil, then I can use these two equations. I said that take care that in this equation for the active zone I have a negative sign. This negative sign has a major effect on having something special, which is the crack. If I have a C soil here, so the contribution of the phi here is 0. I don't have phi in the equation. So it is only C that is working. So I will start with, here the vertical pressure will be 0. So it is only negative due to C. So in this case I will have negative pressure on the wall. Negative means the wall is not pushing, the soil is not pushing the wall, but the soil is going away from the wall. Once I go below, the overburden pressure starts to increase. This increase starts adding a contribution of the phi in my equation, so that the phi here starts to, this term start to increase till I reach a location where this term equal to this term. This will be this location where I have a 0 pressure. Once I have a 0 pressure, I start have a positive pressure on the wall. So it is very important to have this critical, H critical, which is the end of the crack or the separation that will happen between the soil, and this is the shape of the soil once it retreats back away from the wall. Starting from this, I will have my pressure here. In the other direction, I will still have the passive. My passive will be standing here as it is, but my active will start from this point, not from this point. For you, as I said before, in case, of course it's not the scope of the exam, in case I have rain, water will come fill this place. So in this case I will have to add the effect of a triangle of water that will push the wall here. But this, just you need to know it as an engineer. And so on. You have how to calculate H critical, calculated by any way, by drawing, by equation, the equation that is given here, calculated by trigonometry, whatever the method you are going to use. calculate the H critical, and this is important. Which points I'm going to calculate? As a rule of thumb, you calculate at the beginning of the layer and at the end of the layer. At the beginning of the layer, at the end of the layer. Here, why do we calculate 3 and 4? 3 is the same depth as 4, but 3 belong to layer number 1, 4 belong to layer number 2. Here I have C and phi, here I have another C and phi, so I need to calculate at this elevation twice, 1 centimeter above and 1 centimeter below, so that I go into soil number 2 and calculate the value. So I will always at the beginning, at the end, beginning, end, beginning, end, and at any modification in the soil. This is a modification. Groundwater table is here, so it means though I have here C and phi similar to this C and phi, but the vertical overburden pressure will start to change, because here I can use the normal gamma submerged that is given, or the gamma bulk given by the in the example, but here I will use gamma submerged because it is below water. Of course here it will be gamma submerged also, and here it will be gamma submerged also because it is below, but here I have gamma bulk at the top and gamma submerged at the below, and so on. Look at the examples, see what we usually do in solving this example. Of course, you have to know an example for retaining wall by heart. It is very easy, very straightforward. You just get the stresses at point 1, 2, 3, 4, 5, and so on. Change these stresses into forces. Check the stability of the wall. Are the horizontal forces pushing in this direction more than the resisting forces resisting in the other direction, or I have a factor of safety, and so on. Am I going to take the passive in my consideration, or I am going to calculate the friction between the base of the wall and the soil? You have many examples, 2 or 3 examples here. Check them. Of course, this is the case of the sliding. This is the case of overturning. The force that I have calculated, it may turn the wall. How is it going to turn the wall? With a moment. Multiply this force with this distance from here to there to get the moment, and so on. You have a moment in the opposite direction, calculate the factor of safety, and so on. There is another check for the bearing capacity, and I always say that it is not the most important one. The most important one is the sliding, then the overturning. The bearing is not very important because calculation-wise it is very complicated. But of course you can do it with a computer, but I'm speaking about my exam, I'm speaking about our courseworks. But in case I have a little bit of failure due to bearing, what will happen? What will happen is that the wall is going to move below a little bit. Maybe it would move 5 centimeters below, 10 centimeters below. Is there a problem? No, just add in the length of the wall another portion, so this will compensate for the settlement that will happen to the wall. So this is what we have. Check your examples. Our problem is usually straightforward. Just check what is given here. These are 3 examples. In this last example, instead of giving you the dimensions and telling you to calculate the factor of safety, here there is one missing dimension, which is the B. But you have all other dimensions and you know the factor of safety. So based on the factor of safety of each category, factor of safety for sliding, factor of safety for overturning, factor of safety for end bearing, we can calculate 3 values or 4 values depending on the equations for the B. And once I calculate the 4 values, I get the the maximum value of B, because the maximum value of B will satisfy all the conditions that I have said here. This is a quick review. Starting from here, this is an example. So you see, in case of end bearing, checking the bearing capacity, this is the type of the equation. It is equation maybe a little bit complicated. It is not the scope of our exam. We also took a chapter for the shoring systems. It has no examples. Chapter 8. No. It is more or less a retaining wall, but it is temporary, as we said before. We also took the reinforced earth. It is more or less a retaining wall, but it is for the walls that will be the soil that will be constructed in the future, not for existing soil. And it is it's not expensive, so it can be used in many projects, and it is durable and very good. This ends up our lecture for the revision. I hope that you go through all of our lectures. The revision lecture is not adequate for the study. You should refer to each lecture and see what is written or what is given. Thank you, and see you next time.